Lecture, let us talk about function of two random variables. First, we'll talk about one function of two random variables. Later on, we will see the two function of two random variables. So previously, we have talked about the function of one random variable. So in that case, if we know the PDF or the CDF of one random variable, then we can find the PDF and the CDF of a new random variable, which is the function of the old random variable. So the one function of two random variable, here we can see example. It could be sum of two random variable, could be difference of two random variable, it could be a product of two random variable, it can be divide two random variable. So it could be the maximum or the minimum of two random variable. So okay, let's talk about one function of two random variable. So x and y are two random variable. So a new random variable which is the function of x and y. Given the joint PDF of f sub xy, how does one obtain the PDF of a new random variable z? So here we first know the PDF of the joint PDF of two random variable, and we will find the PDF of new random variable z, which is the function of random variable x and y. So the practical example could be a receiver output signal usually consists of desired signal buried in noise. So when you transmit a signal, so at receiver end, it is buried with a noise, a new signal, a noise add with the original signal. So you get a new signal which can be formulated by two random variables. So a new signal z, which is the function of some original signal x and some noise which is added into the original signal. Now move to some example. Okay, now the CDF of a new random variable function z, a new random variable z, which is equal to the probability of z, which is less than some number z, which is equal to the probability of function of x y less than equal to small z. So also equal to the probability of x and y belongs to the domain of z. So in other word, we will integrate along x and y axis the PDF function, the joint PDF of x and y. Here d sub z is the range of a new random variable z. So first we have to find the region of sub z for every z, then evaluate the integral. Okay, so let's talk about some example. A function of a new variable z, which is the sum of old random variable x and y. We have to find the PDF of a new random variable z. So first let us define the CDF, the cumulative distributive function of random variable z, which is the probability of x plus y, which is less than or equal to z. So what we will do, we will integrate. So there are two ways. I mean, this strip show the region. I mean, this strip show the region which describe the new variable z, which is equal to we can write z is equal to z is sorry. We can write z is equal to x plus y. So there are two ways this integral can be solved. So first we will take a strip that is from infinity to this point, which is x is equal to y minus z. Or other way, we can take a strip from along the vertical direction from minus infinity to this point, which would be equal to y is equal to z minus x. So first we will integrate. We are taking the strip from minus infinity to some point x is equal to z minus y. So here we will integrate from minus infinity to some point x, which is equal to z minus y. So here is the limit of x is from minus infinity to z. So you should be careful about this limit. You are integrating it from along x direction. So the limits for y would be from minus infinity to infinity. So integrating over all horizontal strip like the one in the figure along the x-axis, we can find so by differentiating this CDF, cumulative distributive function of z, we will get the PDF of a new function and the new random variable z. So now in next step we will differentiate these expression. So move to the next slide. For this, first we have to recall the Lebanese differentiation rule. In Lebanese differentiation rule, there is some h of z. There is function. Here is a function which is equal to integrating this function from a to b. These are the limits. So when we will take the derivative of this function, so this would be equal to the differentiation derivative of upper limit z with respect to z, upper limit b with respect to z into that function. And here we will substitute instead the limits of x, which is the upper limit of x. Then minus, we will take the derivative of the lower limit with respect to z. Then we'll incorporate here in this function the limit. We will incorporate the limit of the x. So in the third term we will integrate it. We will take the derivative of this function with respect to z, and we'll integrate from a to b. I'm not going to prove this Lebanese differentiation rule. You guys are already familiar with this rule. Now when I will differentiate this function, so I will apply the Lebanese theorem here. So by applying the Lebanese theorem, so the first term here, which is a constant, which is y minus z. So by differentiating the upper limit, this, when we will differentiate with respect to z, this would be equal to 1. So I will multiply with this function. So by differentiating the lower limit, so which is a constant which will vanish here. So I will get the expression f sub xy. So here we will incorporate the upper limit, and so this function, we will get this function, it will multiply with. So here uh, will multiply with the 1. uh, this term will multiply with the 1, so there will be no effect on this term. So this term will vanish, as I already said, that the derivative of this constant is 0, so this will vanish. So the third term here, so I can write it as by differentiating with respect to z, this will vanish. So I will get this term, which is from minus infinity to plus infinity. So this is the PDF of the new random variable z. Now next, we can find if the random variable x and y are independent, so we can write this term. So this PDF, already we know that this PDF f sub xy, this joint PDF, would be the product of, sorry, I can write it as this, the product of f sub x and f sub y, the marginal PDF of x and marginal PDF of y. So we can see the PDF, we can write it as so this is the alternate way. In alternate way, we can take a strip from minus infinity to this point, y is equal to z minus x. So first we will integrate along x-axis from minus infinity to infinity, then along z direction, axis, we will integrate it from minus infinity to this point, y is equal to z minus x. So again, to find the PDF, we will take the derivative of this CDF. So this expression can be solved by Lebanese theorem. We already know. So first, we will take the derivative of this upper limit and we'll multiply with this function. So the derivative of this z, that would be equal to 1, so it will multiply with this function. So the derivative of next lower limit would be equal to 0, because this is a constant. Then third term will contribute. So eventually we will get this term from x is from minus infinity to infinity. So this is the PDF of a new random variable z. Now as I already told that x and y are independent random variable, so in that case the joint PDF of random variable x and y is equal to the product of marginal PDF of x and PDF of y, as we already know that in case of independent variable we can write in this way. So by incorporating these terms, so in case of independent random variable, I can write it f sub x into z minus y into f sub of y into d of y. So in alternate way, I can write f sub x of x into f sub of y z minus x. So in both way we can write it, write the PDF of z. So this is the, we know this is the convolution of two PDF, PDF of x and PDF of y. So we can say that the sum of two random variable, independent random variable, their PDF would be the would be the convolution of two PDF. I mean the convolution of Okay, we can write the sum of two random variable in term of the convolution of the PDF of two random variable as in this case. So again, the region in this case, the region would be the area under this curve. So this whole region would will give the CDF of the new random variable z. Now let us talk about another example. So here is the conclusion of this example. So this is the CDF of new random variable z, which is the sum of random variable x and y. So sorry, in this case, if x and y, so in this case, now let us talk about. So here in this example, if x is less than 0 and random variable y is less than 0, so in this case we can write the new random variable y should be less than 0. So in this case the limits would be for along this strip. So the limit along the x-axis we can write from in this example. Let us consider, we are considering the case x is greater than 0 and y is greater than 0. So in this case, I mean x is positive and y is positive, so the limits would be for x, if we take a strip along x-axis, so it will start from 0, it is greater than or equal to 0, so it will start from 0 to x is equal to z minus y. So the limits for y would be from this would be from 0 to z. So the expression for the CDF, so the CDF of f sub z would be equal to, so for along y-axis we will integrate from 0 to z, and for x-axis we will integrate from 0 to z minus y. So the PDF of new random variable z would be, we will take the derivative, differentiate with respect to z. So after differentiating I will get this expression. So here we will apply the Lebanese theorem. So after solving this expression, I will get the integration from 0 to z and f sub xy, the joint CDF, z minus y comma y. So when z is greater than 0, otherwise when z is less than or equal to 0, this PDF would be equal to 0. Now for taking the vertical strip, so this solution we can write in this way. Furthermore, if x and y are independent, so there the PDF can be write in term of the PDF of new random variable z is in the term of the convolution of the PDF of random variable x and random variable y. So this is possible in the case when x and y are independent random variables. Further, in this case, the cumulative distributive function would be the area, I mean in this region. So let us talk about another example wherein x and y are independent random variable with common parameter lambda, and x and y, the PDF is the exponential function of f sub x and f sub y. The PDF of random variable x and y is the exponential function. Now the PDF of a new random variable z, which is the So here we will apply this formula. This is the extension of this problem is the extension of this problem. So here, by applying the convolution formula, I will plug in the PDF of the marginal PDF of random variable x and marginal PDF of random variable y. So by plugging in the PDF of x and y here, so I will get lambda square into e raised to power lambda z. So by integrating from 0 to z, integrating the d of x, so I will get these expression. I think we should finish it here. So next in next class I will continue this lecture, and we will further we will see the two function of two random variable.